The next thing to talk about, this is another rule for composite functions, but this time I really mean the composition of functions, functions embedded inside of other functions. A fairly easy to understand example is sine of x squared, where x squared is embedded inside of sine, and we often say that this is the composition of sine of x with x squared. So sine of x is the outer function, and x squared is the inner function, and to use the chain rule, you will need to be very familiar with what is the inner function and what is the outer function. And sometimes, unfortunately, in mathematics, the notation doesn't make that completely transparent. So to talk about a couple examples, here is a composite function, or a composition of two functions. The outer function is the square function, and sine of x is inside of it. The notation kind of obscures that fact, but really this is the same thing as sine of x squared. And so sine of x is inside of the squaring function, so to speak. Now, in the next one, it's a little bit more transparent. The outer function is ln, the inner function is sine, and so that's that. In the next one, it's a little less transparent. If we wanted, we typically want to talk about the outermost function, right? So here, you could say that the outer function is e to the x, and the inner function is sine x, sine squared x, sine squared 4x. That's the inner function. But that's not the only way to chop this thing up. We could say that the outer function is the outer function is e to the x squared, and the inner function is sine of 4x. And there's even another way to chop this up. So, sometimes you will have many ways of decomposing a function into inner and outer functions, and typically what you really want is to identify the outermost function. So the first way that I discussed is the way that you want to think about things for the purposes of the chain rule. So here we would regard this as the outer function being e to the x and the inner function being sine squared 4x. So with that having been said, let's also just say a little bit about notation, a little bit more. This is also how we write composition of functions or embedding of functions when we have these sort of generic names for functions, f and g, or sometimes we write it with the little circ notation. So if we say that f of x is sine x and g of x is x squared, then we could rewrite sine x squared as we are putting x squared, which is g, we're putting g inside of f. That's an equivalent expression. Now, I have said in this example that sine x equals f of x, and you might wonder, is that the same x as the x that we have here? And the answer is it doesn't matter, in fact, because we're replacing it at the end of the day. So the variable that we use inside of f when we state this really just doesn't matter, because we're going to get rid of it in a minute anyway. I might as well just call it x just so that I don't have a bunch of different confusing letters all over the place. Although you could call it you could call it y, you could call it z, you could call it anything you want. It doesn't matter because we're going to replace it. So in any case, now let's state the chain rule. The chain rule is actually one of those rules that students typically find very challenging, and so I have my own kind of quirky way of handling it that I hope makes things easy on new students. So I have what I call this tabular method. And really the table just kind of collects together all of the information that you will need in order to use the chain rule. So, okay, enough dancing around it. What does the chain rule say? The chain rule says that if you have a function composed inside of another function, that the derivative of this composition is you take the derivative of the outermost function, plug back into it the inner function, multiply the whole thing by the derivative of the inner function. Now, as a quick, somewhat helpful way of saying that, you take outer prime, plug in the inner times inner prime. So that's how I state that. And a lot of people find this a sort of easier expression to work with. So so let's actually use it. Let's actually calculate the derivative of sine x squared, the example that we've been working with so far. So the outer function, as we've said, is sine x. The inner function is x squared. We take the derivative of each of those, because we will need it, and here's what we do. Use the derivative of the outer function, plug in the original inner function. So that gets me cosine x squared, and that's the first factor. Then I multiply that whole thing by the derivative of the inner function, and that's 2x in this example. So here is the derivative of sine x squared, or we could rewrite it this way if you care to. Okay, that is the statement of the rule, and now I'm going to go into the proof, which as always you can skip if you want. The rule can be somewhat intuitively justified or motivated by using Leibniz notation and just kind of, in the derivative, or I'm calling f of g of x, I'm calling that h of x, just to kind of keep things simple, right? Use the fewest number of symbols that I can use to keep the picture kind of clean. And I'm calling g of x equal to u. And so if we're looking for the derivative of the composition, which is h, then it makes sense that if you're trying to find the derivative of this, you might just slip in this du on bottom here and on top here, and sort of imagine that these two numbers cancel in the multiplication of fractions. Now, this is a rough argument, but it, more or less gets the idea right. Now, I'm going to use this to develop my proof. And in fact, I'm not going to give a fully rigorous proof, because a fully rigorous proof is hard and is more appropriate in a real analysis course. But here is a half rigorous proof, and I'll point out the step at which it's not completely justified and in some instances would not actually be justified. So I start with just the statement of the derivative, as always, and but here I have just generic functions f and g. Now, if I want to work in the change in u, which is to say the change in the inner function, because I used u to denote g of x, this is our expression for the change in g, right? It's what you would see in the statement of the derivative of g, which is that part of it that represents the change in g, right? H represents some kind of change in the horizontal coordinates. This represents a change in the vertical coordinates. So this is kind of like du, the change in u, or the change in g. And I want to work it in somehow, kind of like how I have here. So I multiply top and bottom by that, and then I rearrange, right? That's kind of how these things tend to go. So I take the denominator here, and I group it with this thing, but in fact, I want to wrangle this thing. I want to manipulate it in such a way that it looks more like the derivative of f. In fact, I want it to look like the derivative of f with g inside of it, which it's getting close to looking like. But I have to do a little manipulation, which is here, and I'll cut off the video here, let you sort of look at it, let it sink in, and continue the proof in the next video.